Now let us discuss the properties of the Riemann tensor, and also, well, these properties will follow by product. Also, we will see the power of the trick that one uses in the use of locally Minkowskian reference system that was introduced before in this lecture. So locally Minkowskian reference system, where I remind you G mu is equal to eta mu plus corrections, subleading corrections, and gamma mu nu alpha is equal to 0 plus subleading corrections. So let us fix this reference frame in around an arbitrary point. Then Riemannian tensor, from its definition, because gamma is 0, but its derivatives are not necessarily 0, then this guy is d alpha gamma mu nu beta minus d beta gamma mu nu alpha. Or, which is the same, after plugging in expressions for gamma, is 1/2 of d squared nu alpha g mu beta minus d squared nu beta g mu alpha minus d squared mu alpha g nu beta plus d squared mu beta g mu alpha, where we have introduced a notation that d squared alpha beta is just second derivative, d alpha d beta. So this is how Riemann tensor looks in locally Minkowskian reference system. As you see, if the space is curved, it means that the first derivative of gamma doesn't vanish, means that the correction to these guys is of order of psi, and the second derivative of the metric doesn't vanish, which means that the correction to this is psi squared. So that's exactly the point. That's exactly the reason why we have these corrections in case of the space. So these guys, metric is equal to this eta mu only if the space is exactly flat around that point, and gamma is equal to 0 then. So that's an important comment. But now, from this form of the metric, of the Riemann tensor, it is not hard to see its properties. We already noticed that Riemann tensor changes its sign under the exchange of these indices. That's already have been used before in its definition. Also, now from this form one can easily see that it is also antisymmetric under the exchange of its first couple of indices. But also one can easily see that if one exchanges the pair of indices, so I mean this couple with this couple, it doesn't change its sign. And the last equality that one can observe from this expression for the Riemann tensor is as follows, that R mu nu alpha beta plus R mu alpha beta nu plus R mu beta nu alpha is 0. Differentiating this expression with covariantly differentiating this expression, one can obtain the following relation for the Riemann tensor, which is as follows: the mu nu alpha beta covariant derivative with respect to gamma plus R mu nu gamma alpha covariant derivative with respect to beta plus R mu nu beta gamma covariant derivative with respect to alpha is equal to 0. Now we have obtained all these relations from this form of the Riemann tensor. Means we have obtained it in locally Minkowskian reference system. But these relations are tensor relations. They relate tensor quantities, those quantities which transform multiplicatively under coordinate transformations. It means that these relations will remain the same in any other reference system, although they have been obtained only in this reference system. It means that these relations are always valid, always in any reference system. And this relation is referred to as Bianchi identity. Bianchi identity. Now, one can, using Riemannian tensor, one can define a new quantity. First of all, if one will contract index first couple of indices, say mu mu, contract means to make them equivalent and sum over them, we'll get 0 due to antisymmetry of this guy. But we can contract the first and the third index. Then this will be mu nu, mu beta, and we will obtain this tensor, which is not 0. This is called Ricci tensor. Ricci tensor. Ricci tensor. And this quantity is actually symmetric under the exchange of its indices as a consequence of this relation. So Ricci tensor is symmetric. Furthermore, we can contract indices of Ricci tensor with the use of the metric. That's the usual way of contraction of indices. And we will obtain the Ricci scalar. So this is Ricci scalar, and this is Ricci tensor. Now, if one will contract indices here in this expression, cup this index and this, I mean index mu and alpha, he will obtain the following consequence of the Bianchi identity, that R mu nu mu covariant derivative with respect to nu, it's equal to 1/2 d mu r. This is a consequence of Bianchi identity that we have for the Ricci tensor and Ricci scalar. Notice that this is a covariant derivative because it acts on the scalar. Covariant derivative when acting on the scalar is equivalent to the regular derivative. Now we are in a position to say a few things about the number of the components of the Riemann tensor. Well, we have these relations. We can say that. First of all, like we will do that in arbitrary number of dimensions. Although so far we have been considering 4-dimensional space-time, let us consider d-dimensional space-time. Then, basically, in any manipulations that we have been making during this lecture, we never use the number of dimensions in space-time. So whatever we have been saying is valid for any d. And in fact, for any signature of the metric, not only in Minkowski and also in flat space, etc., etc. So far. Now, let us find number of the independent components of the Riemann tensor. Due to this antisymmetry property, we have d times d minus 1/2 number of combinations of mu nu and alpha beta for each of them. At the same time, due to this symmetry property, we have the following number of whole combination of these indices. It's 1/2 of this times d minus 1 over 2 plus 1. So this is a total number of independent components of Riemann tensor according to these symmetry properties. But we have this relation. To find number of these relations, so let us consider this quantity. Let us consider this. Let us denote this as b mu nu alpha beta. This sum as b mu nu alpha beta. And it is not very hard to observe that this quantity is actually totally antisymmetric on the exchange of any couple of its indices. So let us see that immediately from here using these properties. So it's not hard to see that b mu nu alpha beta, which is by definition this quantity, it is equal, after exchange of the indices, it is equal to R nu mu alpha beta minus R nu alpha beta mu minus R nu beta mu alpha, and it is equal to minus B nu mu alpha beta. Similarly, one can check that it is antisymmetric under exchange of alpha beta, nu mu, etc., etc. So it means that this is totally antisymmetric tensor. It means that this relation establishes the following number of conditions. So it reduces the number of quantities, independent quantities in Riemann tensor by the following amount. We have the following number of conditions here. D times D minus 1, D minus 2 times D minus 3 over 4 factorial. This is a number of relations of this sort. So we have to subtract from this quantity, this quantity. As a result, we obtain D squared minus D squared minus 1 over 12. That leads, in 4 dimensions, this is 20 in 4 dimensions, 4D. In 3 dimensions, this is 6 in 3D. And in 2 dimensions, this is 2 in 2 dimensions. But we can use, in principle, in locally Minkowskian reference system, around any point, we can reduce this amount even by a bigger, using the symmetries, using extra symmetries, which are d times d minus 1 over 2, number of Lorentzian and Lorentzian transformation and rotations. The total number is this, which is 6 in 4 dimensions. This we have been already counting before. So using this number of symmetries, we can even reduce this number. So we have smaller number of independent components of the Riemann tensor in this dimension, smaller than these given numbers. So those are the properties of the Riemann tensor. In the upcoming lectures, we are going to use Riemann tensor to define, and the other tensorial quantities, to define equations of motion in general relativity, and to use these equations in studying the physics. So far, that was just geometry of curved spacetimes.